Good morning and good evening, everyone. Are there anyone?
Good evening,
Good
ma'am.
evening.
Good evening. And normally, how many participants are there every day? Means how many have enrolled for this course? Do you have any idea? So that we can just start our class today. Means is this the means only 6 or 7 participants are there, or we can wait for some others? Can anyone tell about that? Am I audible or not?
Yes, ma'am.
Okay. So how many participants are there? Do you know?
Uh, 4 participants, ma'am. 5.
Every day this only 4 students.
Yeah, ma'am.
Okay. Uh, all are from Odisha or anyone from outside Odisha?
No, I am from Calcutta, ma'am.
Okay, you are from Kolkata. Okay. Okay. No problem. Then we can start our today's discussion. Okay. I'm
Okay,
just
ma'am.
sharing my presentation. Just let me know if it's not visible. So, is it visible now?
Yes,
Yes,
ma'am.
ma'am.
Okay, good. Myself, Dr. Suman Sahu, actually, uh, I am a lecturer in Raurkela. So, I would discuss mostly your uh, this MCH-012, which includes the stereochemistry and reactive intermediates. And this module has 4 units, which is stereochemistry 1, stereochemistry 2, then reactive intermediates 1 and reactive intermediates 2. And you all know that every class, like every day's class, is about one block. So today we will discuss about this stereochemistry 1. Okay, so before going to this detail into stereochemistry, we should know that what does it mean. So stereochemistry is actually deals with the stereoisomers and how we get stereoisomers in our compound and reactions and many asymmetric induction and many different parts are there. So it deals with mostly the stereoisomers, how it is prepared, how we name it them, and all these things go on. So first we should know what are our stereoisomers. So stereoisomerism, before going to that, we know that isomers, what are isomers? So if this compounds have same molecular formula, okay, then we say, tell them as your isomers if they have the same molecular formula. Okay, so if they are connected in the same order, then we tell them as your stereoisomers. If they are not connected in the same order, we just tell them as our constitutional isomers. Then we have functional, positional, skeletal. Those are different. But if the atoms in that compound are connected in the same order, we tell them as your stereoisomers. Again, if these stereoisomers are of 2 types, one is your configurational, another one is your conformational. So if these stereoisomers or if these stereoisomers can be interconverted from one isomer, we can go to the other isomer by just rotation about our single bond, then that is known as your conformational isomers. So mostly those are in case of your single bonded compound, so you can just rotate it to go from one isomer to another. So this is basically same molecule, we get different uh, isomers, and depending on the conditions, temperature, pressure, and etc., we would have different isomers of it. And some may be stable, more stable, some may be less stable, as we will deal with in case of our cycloalkanes, alkanes, and all those. So that comes under your conformational isomers. And if you cannot interconvert those isomers by rotation about single bonds, then those are known as your configurational isomers. This configurational isomer is again of 2 types. One is your geometric, one is your optical. Geometric isomer comes in case of when we have a double bond. So this is a kind of cis trans isomer. If same group on the same side, that is cis on opposite side, that is your trans. So if the isomer is configurational isomer which cannot be interconverted by rotation about single bonds, in that case, if the geometric isomerism is restricted due to rotation due to its double bond, that is due to your restricted rotation, then that is known as your geometrical isomers. And optical isomers comes when these compounds show optical activity, that is it rotates the flow polarized light. So those are non-superimposive plane polarized light. Again, this optical isomerism is of two types. One is your enantiomers and diastereomers. If their mirror images are non-superimposable mirror images, then we would just say that as enantiomer. Those which are actually related to each other by mirror images, and which are not actually related by mirror images, we tell them as your diastereomers. Even these geometric isomers are also known as your diastereomers. That is, those are not mirror images. They are stereoisomers, but they are not mirror image of each other. Those are known as your diastereomers. Okay. So in organic chemistry, actually we know that carbon is a tetrahedral, means it has four valency, tetravalency. So the structure is tetrahedral, which is a 3D represent, which is a three-dimensional molecule. But whenever we are dealing it in a plane of paper, then we have to represent in two dimensions. So we can represent in many type of representation. One is your flying wedge representation, in which actually we have a simple line like this, blue lines, blue bonds, and we have one solid wedge and one gassed wedge. So which one? These blue lines, these are in the plane, this hydrogen, carbon and hydrogen, these three are in the plane of paper, and the solid wedge is actually towards the observer, and the gas wedge is away from the observer. Similarly, we have a zigzag representation also. We can do like this, and we can view in a Fisher projection also, where the center, the atom we are just showing, that is in the center, and the horizontal bond shows that these are out, this like the central atom is in the plane of the paper, and the horizontal bonds are towards the observer, and the vertical bonds are away from the observer. And also we can have a sawhorse representation, in which we just look down this carbon carbon bond. Okay, so in this carbon carbon bond represent, this sawhorse representation, first we just put a, suppose we are going for this one is our ethane, so we just do like a slanting line, then we just look it through this carbon. So you don't have to write carbon here, then you just have to put the substituents, and this is, we can put these hydrogens or whatever substituents there in such a way that they are just in a eclipsed conformation or in a staggered conformation. Eclipsed means like in case of our solar eclipse or that. So that means I would say that this one is your eclipsed conformation. As you can see, this one is just hindering the site of this CH3 group. This hydrogen is hindering the site of this hydrogen group. We cannot, if we just see from this, we cannot just see this hydrogen, we cannot see the backside hydrogen. Okay, so this one is your eclipsed conformation. If we rotate this, then we have a staggered conformation, which here where all the substituents are visible, and there is less repulsion. Like in case of your this one is your Newman projection formula. In Newman projection formula, you see the blue dot, the center, that one is your front carbon. Okay, and the circle, we are not the middle of that circle, that is in the back carbon, and the attached atoms are shown like this. So in case of staggered conformation, as you can see, uh, the they are as far away from each other as possible. If we just see in this case of your butane, this CH3 groups, we will see the conformational isomers later on, but just for Newman projection formula, as you can see, this one is our carbon number 1, this one is your carbon number 2, and the backside carbon would be carbon number 3, this one carbon number 4. So 1, 2, 3 and 4. So this is represented in such a way that the front carbon is at least means these 2 3 are just showing the middle carbons we are just showing, and these two are like the substituents, and 2 is your front carbon, and cs3 group is present here as a substituent, and this is the staggered configuration. If we just rotate it, then we would get your Sawhorse projection formula. The in Sawhorse projection formula, as you can see, the Sawhorse projection formula, the it is easier to represent. Like if you put two y's like this, then that is your eclipsed. Just rotate another, then that would be your staggered conformation. So these are the Sawhorse, Newman, Fisher projection formulas. So how you convert from one projection, because whenever they ask you about your configurational isomer or something to detect that, then it might have asked you in Fisher projection or in other projection formula, then you have to predict the configuration of that one. Then you have to convert it from one Fisher projection to another projection. Actually, these all have been taught in your graduate level. But still, this is just, I am just brushing up your memory. So whenever we have to convert a Fisher projection, in case of Fisher projection, as you can see, the carbon chains are always are in a vertical position. Okay, so when we convert a Fisher projection to Sawhorse, so first you have to do it from the Fisher to your eclipsed conformation. Okay, so this one is your eclipsed conformation. So just 2 3 carbon, you put a slanting line, and you start from the below, means down the not from the top, from the down carbon. So this is CH3, and the other CH3 in this one, it is here. And uh, this says the left hand side you have bromine, and here you have left hand side bromine, and right hand side hydrogen. Similarly, here you have hydrogen on the left hand side and bromine on the right hand side. So this gives you your eclipsed conformation in Sawhorse projection formula. So when you rotate this one, just keep this one constant, you rotate it 180-degree rotation. This bond you rotate it, this bond you rotate, so that this hydrogen will just, it was here, so it will come to here, and this CH3 is here, so this will go there, and this bromine is here, so that it will come here. So that gives you a staggered conformation. Similarly, you can convert Sawhorse to Newman, and conversion of Fisher to also Newman in this way. For example, from Sawhorse to Newman projection formula. So as this one, we can see this one is a staggered conformation in this case, and this is your front carbon. Just put this one is your front carbon. Phenyl, bromine on the left side, OH on the right hand side. And on the back carbon, this is our back carbon. On back carbon, if you just see, this is the staggered conformation. Staggered conformation means pH and CH3, they are on opposite sides. So put CH3 here, OH and NH2 are on opposite sides. So our OH is here and NH2 is on this side, and bromine and Cl, they are on opposite sides. So that gives this staggered conformation in case of a Newman projection formula. So now if you rotate it, keep the back carbon constant, just rotate the bond in 2 3 bond, so that keep the conformation, means the positions of your back carbon same, just rotate it 180-degree, so that this one will come, this phenyl will come just to near your CH3 group, and this OH will come to just opposite, it will come to NH2, and this bromine will come beside your bromine. Then you can just again go to your Fisher projection, in which this one is our now front carbon, so phenyl CH3 and OH is on left, bromine on right, NH2 on left, chlorine on right. So you can just interconvert the projection formulas from Fisher to Newman, Newman to Sawhorse, like that. Okay, so before going for stereoisomers or mm, asymmetric, dissymmetric. So we should know some symmetry elements, like in your group theory, maybe in your inorganic classes, you might be reading all these things. So there are many type of symmetry elements and symmetry operations. One is your rotational axis of symmetry. You can rotate a molecule and by any time, so that you are going to get the same type of configuration. Suppose in this case, as you see, if I rotate it through this one, then first rotation will give me this one, and the second rotation will give me the exactly same as the initial one. So this has a twofold rotational axis of symmetry. Means when I rotate it twice, then I am getting the original compound. Similarly, we have a plane of symmetry. So just you see in this molecule, this is a plane of symmetry. Like if I check this is exactly similar on both the sides. We have the same substituent, so this has a plane of symmetry. Similarly, in case of this 1,1 dichloroethane, if you just see, if we put a plane through this carbon-carbon double bond, the upper half is exactly equal to the lower half, so that is known as your plane of symmetry. Similarly, we can have other one is your center of symmetry. In case of center of symmetry, when you go from one uh, point or one group to another, passing through the middle of your compound, means center, then you are going to exactly end with the same type of group or atom, then that is known as your center of symmetry. As we can see, in case of 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid, that gives a center of symmetry. If we go from this COA2H group and we go pass through this, and we are ending up with the same type of group, so that is known as your center of symmetry. So, and then another one is your alternating axis of symmetry, in which, like, actually alternating axis of symmetry is you rotate a molecule by 90 degrees, 60 degree, or 180 degree, and then you just take the mirror image of it. Then that is, if it is going to give you the same, exactly same as your initial, exactly same conformation configuration, exact, then that is known as your alternating axis of symmetry. So how does these symmetry elements and symmetry operations are taken into account in our stereochemistry? So if we have a alternating axis present, and simple axis may or may not be present, then that term is known as a symmetric. That molecule is symmetric. And when we have a alternating axis is absent, but a simple C2, C3 axis is present, then that molecule is known as a dissymmetric. These are usually active, optical active. What is optical activity? I will come now. And asymmetric, where you do not have any alternating axis of symmetry or any axis of symmetry, then that molecule is not known as your asymmetric. But this dissymmetric and asymmetric, these are usually optical active, so these are, we can say these are your chiral molecules. So what is this optical activity? Optical activity is known as whenever we uh, uh, pass a plane polarized light through a solution of this molecules, so through these compounds, if that rotates the plane polarized light, then those are known as your optical active. If like, what is plane polarized light? In our normal light, it is actually directed to all the directions. So we have a polarizing filter which just removes all other directional lights. Only one light, only in one plane we would obtain that light, so that light is known as your plane polarized light. So when this plane polarized light is passed through any of these compounds, if it is have dissymmetric or asymmetric, it is going to change the plane, like it is in this direction. If it is going to going through one enantiomer, I will come, what is enantiomer, what is a diastereomer. Okay, so if it is going pass through an asymmetric compound or dissymmetric compound, the plane polarized light is going to rotate either in clockwise direction or in anti-clockwise direction. If it rotates, means it should be in this way, now it is in this way, then that is your clockwise direction. We write it as plus. If it is rotated in anti-clockwise rotation, then we just say at minus. So when it is rotated in clockwise direction, then that compound we just say this as your dextrorotatory. And when that is that rotate the plane polarized light in counterclockwise or anti-clockwise, we tell that as your levorotatory. Okay, so if one enantiomer, we have the same compound, but one rotate enantiomer, and the condition for enantiomer is one enantiomer rotate the plane polarized light exactly, the distance exactly in clockwise direction would be equal for the other isomer, but in a counterclockwise direction. Suppose your alanine, these two are your enantiomers because they are non-superimposable mirror images. If you just see L-alanine, this one is the mirror image of the other one. And if this rotate the plane polarized light in clockwise direction, then that one would be rotate the plane polarized light in another direction. So these two are non-superimposable mirror images. So those are also known, those the term used is enantiomers. These enantiomers are structures that are not identical but are mirror images of each other. So structures are chiral if they cannot be superimposed upon their mirror images. So just you see your left hand and right hand, they are not superimposable. You cannot wear your left-handed glove on your right hand or right-handed glove on left hand. But these two, this one is the screw, also they are chiral. But this chair, this is a superimposable mirror images. As you can see, the condition is that if you have a plane of symmetry, as case in the case of A and 8, so these are achiral, like their mirror images are superimposable on each other. But when you do not have non-superimposable mirror images, then that is known as your enantiomers. Okay, so first you just see whenever we have four different groups attached to a carbon, then that gives you a stereogenic center or chiral center. In this case we would come in next class that stereogenicity and chirality would be again different. Okay, so for now this is your stereogenic center. uh, but whenever you have three different groups, two are same, then this is not a chiral molecule, but this one is a chiral molecule. So for carbon, for now we have a chiral center when we have four different groups. How we uh, denote, like mm, configuration, whether the OH group is on the left or CN, or the IUPAC name for one enantiomer and for the other enantiomer. Previously, there was one thing that is your relative configuration, or that is known as your DL system of nomenclature. You just in this relative configuration, someone has been being given the standard, and relative to that, the compound under investigation is given your configuration. For example, glyceraldehyde is actually that is the mm, mm, maybe the first or second molecule whose configuration was exactly known. Okay, so don't confuse with this capital L and capital D and small d and small l. Small d and small l gives the rotation of the plane polarized light. If it is in the clockwise direction, then small d, and if it is in the counterclockwise direction, that is your small l. But these are just for its relative configuration. Capital D and capital L for your relative configuration. So according to this DL system of nomenclature, the this is the glyceraldehyde molecule. So whenever this OH group in glyceraldehyde molecule, this OH group is on the left side, so that is L, and that is L glyceraldehyde, and the OH group on the right hand side, that is your D glyceraldehyde. So whenever in any other molecule the high electronegative element is on the left side, then that is given as L configuration, and whenever the more electronegative group is on the right hand side, then that is given as your D term. For example, your lactic acid, so here OH group is on the left hand side, but tartaric acid, okay, whenever you have L-alanine, in case of L-alanine, your among nitrogen and hydrogen, NH3 plus, N is more electronegative and it is on the left hand side, so this is L-alanine. But in case of this lactic acid, OH group is on the right hand side, that is more electronegative, so that is given as your D-lactic acid. And what is the main drawback is that whenever you have two or more stereo centers, for example in this case glucose, okay, so here you have many stereo centers, 1 2 3 4. So here they just check the lowest, the down, or the first chiral center from down the papers. So in that case, whatever be the configuration of that center, the name is written accordingly. For example, in case of glucose, the actually which is available naturally, all the carbohydrates are D, because OH group is on the first. This carbon has OH group, which is more electronegative on the right hand side and H on the left hand side. And all naturally occurring amino acids, they are of L configuration, because you just see everywhere you have NH2 group on the left hand side and hydrogen on the right hand side, or similar type of groups when means similar to OH group, that is on left, then that is L, and when it is on the right, that is your D. So the drawback is that we cannot assign configuration to this other three carbons here in case of your carbohydrates, glucose molecules. So this relative or real system of nomenclature has many drawbacks. Then comes our RS system, that is your absolute configuration, where some can in gold Freelag rules are determined to actually um, put your R or S on a chiral center to give your absolute configuration. So this one is actually, whenever we write this IPH name, we have to follow this RS system of nomenclature. So how this one is done? This one is means the chiral center. First, you go for the chiral center, and the atoms or the groups which are attached to it, you have to rank them according to atomic number. For example, in this case, our bromine is having higher first, and the first point of attachment first you have to see. So in this case, first point of attachment is bromine, here chlorine, carbon, and hydrogen. Bromine, of course, we know that bromine is having higher atomic number as compared to chlorine, as compared to carbon and hydrogen. Then you have to rotate the molecule in such a way that the substituent ranked number 4, in this case uh, hydrogen, is in the back. That is, already we have it in this molecule. Particularly we have that is in the dashed form, dashed wedge structure, dashed wedge presentation, so that is in the back. So now you have to trace the path from 1 to 2 to 3. If the path follows in a clockwise direction, assign it as R, and if the path follows one counterclockwise when tracing the path from 1 to 2 to 3, then that would be your S configuration. So this is when your ranked 4, atomic number ranked 4, is in the back, that is in the dashed line. So when it is in the plane of paper, or if it is in okay okay so this is I am just showing it in your wedge structured, wedge and dash structure. We can just go for your Fisher projection structure also. So if that group 4 is in the plane of the paper, so like you see in this molecule, fluorine is having higher atomic number. Then comes your oxygen. The first point of attachment is oxygen, so then comes oxygen, then comes uh, CH3 group, carbon, and then comes your 4 hydrogen, which is in the plane of the paper. So now what you have to do, you have to do two swaps. If you swap twice, then the configuration is not going to change. But if you just swap once, then that is going to change. So first you swap the priority 4 group with whichever group is in the back. So you swap hydrogen with CH3 group, single swap. Then you have to uh, do the double swap also. I have just, then you have to here, then you, what you would do, fluorine and oxygen. So now our hydrogen is here, and I would just swap the position of fluorine and oxygen. Okay, so now you just check what is the uh, so while tracing from 1 to 2 to 3, now this gives you counterclockwise, so that is would be S. So you have to do two swaps. If you are going to do two swaps, then this configuration is not going to change, it is going to remain the same. So uh, then we have another uh, method also. In this swapped chiral center, you have to check your R and S. So here it appears to be R, but you have done single swap, so the true configuration is going to be the exact the opposite. So find the opposite, so you are get the S. So first you have to do single swap, and then whatever be the configuration, you have to do the opposite one. Next one, if not all chiral centers are attached to four different carbons. For example, in this case, this is your chiral center, and here all the groups are carbon. Means this is attached to carbon only. So in that case, you have to assign accordingly their next point of attachment. So here, if you just see in this one, okay, in this one, here we have 1 2 3 4 carbons are attached, so I would give as this one first priority, this one would be your second priority. And here our this CH3 group, that is now your, this is of the lowest priority. So there is another rule also, either you can rotate it, swap twice, or just you check whether that is on the dashed line or on the waist solid wedge. If it is in the dashed line, whatever is the path is tracing, then that is going given. If it is clockwise, then R. If it is anti-clockwise, then it is S. But if the your lower priority group is not on the backside, that is on the dashed line, then here also you just check whether this is going 1 2 2 2 3 is giving you which configuration. So this is giving you what 1 to 2 to 3, that is giving you counterclockwise, so this one should be S. But as CS3 group or the lowest priority group is not on back of the plane, back of backside, so then it would be just reverse, so that would be your R. So you can do whatever way you this one is the easy method, and it is almost always you get the good result in this case, correct? So what about your Fisher projection? In Fisher projection, if your lowest priority group is in the vertical line, then you don't have to worry, just check your path, trace your path from 1 to 2 to 3. If it is clockwise R, if it is counterclockwise, then it is going to be S. But if it is in your any of these horizontal lines, the lowest priority group is any of the horizontal line, then here also you trace the path. If it is clockwise, trace the path and then reverse it. So if it is clockwise, then it would be S, and if it is counterclockwise, it would be R. Okay, or you can just switch it like this. Which one would be easier for you? You can do it. Okay, so for example, in this one, you have to first 4 is your already it is in vertical line, so we do not have to worry about it, just we are taking it. So this is your S configuration, because if we trace the path from 1 to 2 to 3, that is going giving us S. So if we just switch CS3 and BR, so first switch, then you have to do another switch. If you do only one switch, that is going to give you R configuration. Now you switch CH to CS3 and CL, that will give you your S configuration. So two switch, first you do two switches, so that your fourth one comes to your uh, lower means on the vertical line. Or you just check whether it is on the vertical. If priority 4 is on vertical line, then that is okay, that would be your regular clockwise R. and anti-clockwise S. If priority number 4 is on your horizontal line, then it would be just the reverse. Clockwise would be S and anti-clockwise it would be R. So you can do as many problems given in your course. Then what are your enantiomers and diastereomers? Okay, when previously we have just here checked only one chiral centers. So we know that enantiomers are the mirror image of each other. So when we have two chiral centers, as you see in these two cases, here we have two chiral centers. So uh, this one, structure 1 and 2, they are mirror image of each other. Similar here also we can write another structure here where both the bromines are on the same side, and these 3 and 4 are your mirror images. And you can just see 1 and 3, they are stereoisomers. Okay, they are stereoisomers, but they are not mirror images. Okay, these two are mirror images and they are non-superimposable, so these two are enantiomers. And these two are enantiomers, they are non-superimposable, so these two are also enantiomers. But structure 1 and 3 and 1 and 4, or structure 2 and 3 and 2 and 4, they are stereoisomers, but they are not mirror images. So these are your diastereomers. When you have non-superimposable mirror images, those are enantiomers. And when they are uh, stereoisomers, but uh, here also the attachment is means to the same carbon, but their orientation is different and they are not mirror images of each other, they are known as your diastereomers. So you just see diastereoisomers, sometimes diastereoisomers are optically active. We will see now in the next some slide. Some diastereomers are optically active, some may not be optically active, but they have different values of, if they are optically active, they have different values of specific rotation. If this one would give you suppose plus alpha, this one going to give you exactly minus alpha if they are enantiomerically poor. And but here they would give different values of specific rotation. This first is different physical properties, but enantiomers give you exactly same physical properties. They have the same melting point, boiling point, solubility, etc. And due to diastereomers, due to their difference in physical properties, as their boiling point is different, you can separate them by fractional distillation or crystallization or chromatographic techniques. Suppose enantium, here also I have just given some examples. So diastereomers may be achiral as these two, which can have a plane of symmetry, as you just see. These two are diastereomers. Okay, here you have a plane of symmetry. So these two are not chiral, but still they are diastereomers and they are stereoisomers. And or they may be chiral, as for example in this case where you do not have any plane of symmetry, but still they are your diastereomers. So again, we have some examples here. As you see, this 2 bromo, 2 chloro, propane. Here we can have 4 stereoisomers among these 1 and 2. These are your enantiomers because 1 is exactly the mirror image of 2 and they are not superimposable. And this 3 and 4, they are also non superimposable mirror images of each other. So now enantiomer 1 and 2 are enantiomers and 3 and 4 are enantiomers. But this 2 and 3, 1 and 3, 1 and 4, 2 and 4, they are your diastereomers. In this epoxide also, you just see these two are enantiomers. And this are also enantiomers, but this one, they are your diastereomers. So from converting one enantiomer to other, both stereogenic centers are inverted. As you see, this one is your S, this one is R, but the other enantiomer, this one is R, this one is S. But in case of your diastereomer, you have to just check these two relationships. This S is same, but you have to just only one of the two is inverted, but you cannot just go from this one to this one by direct rotation. So you have to go through many chemical processes. Okay, so diastereomers are not mirror images, and enantiomers are non-superimposable mirror images of each other. Enantiomers are optically active always, but diastereomers, some it may be optically active or it may not be optically active. Then comes your meso compounds. Suppose we have these two substituents. Here we have these two substituents same, but these groups are different. So when we have the same type of groups here, but still we here we have two chiral centers because these carbons are attached to four different groups. So now you see structure 1 and 2, they are mirror image of each other. We can write another structure like 3 and 4 which are mirror image of each other, but here you can just see the we have a plane of symmetry in just the middle of this one. If you just put a mirror here, the upper part is exactly the mirror image of the lower part. So these two are actually same, and it's if it is R, this one is S. So this compound, although you have chiral centers, but these are not optically active. Not optically active because you have a plane of symmetry. And the upper half actually is the mirror image of your lower half. So as a result of your mutual compensation. So this compound is known as your diastereomer. Okay, this compound is known as your mesoisomer. This is the mesoisomer of tartaric acid. And 1 and 3 are diastereomers, 2 and 4 are diastereomers. Still they are diastereomers, but these ones are known as your meso compounds. So it has which contain stereogenic centers, but are themselves achiral, are called mesocompounds. So there where you have a plane of symmetry. Next comes your racemic mixture. So whenever we know that enantiomers enantiomers rotate the plane polarized lights in opposite direction. If one rotate the plane polarized light in clockwise direction, the other one will rotate the plane polarized light in counterclockwise direction. So if we have these two enantiomers in equal proportions, so the net result would be 0. So in that case, there would be no net optical rotation. So that is known as your racemic mixture. So here we have two enantiomers in equal proportions. If this one we are going to take 2 moles, then that one we are going to take 2 moles. So there would be so here you have, in case of meso, there is internal compensation. That means that is in the same molecule. But in case of your racemic mixture, there is your external compensation. You are taking two enantiomers, so you are getting no net rotation of your plane polarized light. So how we get racemic mixture? uh, just we take equal amounts of both the enantiomers, exactly equal amounts. Suppose S butanol I am taking 0.5 ml and R butanol we are taking 0.5 ml, then 0.5 ml of 0.5 mole also. So that would give us optically inactive. Here you just see we write plus and minus. Never get confused with this plus, minus, and S is its absolute configuration, and plus shows that it rotate the plane polarized light in plus direction, and minus shows that it rotate the plane polarized light in counterclockwise direction. Okay, so first when we mix the enantiomer in equimolar ratio, then we get racemic mixture. Also, if we get a chiral center from an achiral compound, suppose if we do hydrogenation of this alpha keto acid in presence of ranitidine nickel, just do hydrogenation. So now the hydrogen can add from this side or on the opposite side, so that is going to generate a chiral center, but there is equal chance of hydrogen attacking from both the sides, so we would get a mixture of both the enantiomers. So that gives you a racemic mixture. Even in this hydrogenation reaction also, where we are just using palladium catalyst and hydrogen, that gives a mixture of both the enantiomer. If we just take, we would see that one in next class. If we just put some chiral catalyst instead of palladium, if we just do some palladium in some chiral environment, we can get only one enantiomer. But in case of this any normal catalyst, we are going to get a racemic mixture. Also, we can do racemization, in which suppose this butyl phenyl ketone in presence of OH minus or H3O plus, it would undergo a addition reaction and again elimination to give you your again that ketone, but in a actually both the enantiomer we will obtain. So there are different kind of racemization like acid catalyzed enolization, base catalyzed enolization, even conversion in enol back to the keto form. So this gives you your racemization or racemic mixture. Because if you just see this in case of this acid catalyzed enolization, first you are giving this would in presence of an acid, this lone pair will attack this H plus, and then this hydrogen will be lost and you get your enol and H3O plus again. And in this case you do not have any chiral center. So if it is going back to again this one, in this case the hydrogen will now can attack from top side to give this enantiomer, or the opposite enantiomer in which CH3 group here would be here and hydrogen on the dashed wedge. So that gives you a racemic mixture. Okay, even in case of our SN1 reaction also, we know that SN1 reaction takes place in two steps. First, formation of a carbocation, and then the nucleophile can attack the carbocation on both the sides, giving rise to a racemic mixture. So how racemic mixture, because we know that when racemic, mostly only one form of your enantiomer is active in case of our drugs or whatever compounds. So only one form, if we require only one form, then how, if we are getting racemic mixture in our reaction, how we are going to separate your racemic mixture? That is known as your resolution. So resolution, we can do it in many ways. First way is if we resolute with enzymes. So uh, like this insect pheromone, which is our racemic compound we are often from the synthesis, if we just do the resolution in presence of a enzyme, that is pseudomonas cepacia lipase, that gives you actually this is a only one enantiomer of it would be attacked by this enzyme to give you an alcohol, and the other form remains intact, that is not being changed. Now these two are different compounds, you can just change you can just separate these two forms, and this again can you can, if you need it, you can do esterification and get your plus, means the other isomer. Even formation of diastereomeric salts. So when we have the mixture of both the enantiomers, R acid and S acid, we uh, just uh, we just chemically modify it, or we just react it with another compound of enantiomeric purity. Suppose these are acids, we just take one base which is having S configuration. So now this one is R, this one is S, and this one is S. So these two are that form a RS salt or and an SS salt, and these two are diastereomers. Now only we have studied that diastereomers differ in boiling point, many physical properties. So we can just separate these two by your fractional distillation or by any physical means. So that means then we can go again back to your R acid and S acid. Uh, yeah, here you just say we have RS salt plus SS salt. You just separate it by many means, then you can go back to your R acid and S acid. So this is by formation of your diastereomeric salts. Next, chromatographic separation. Actually, chromatographic separation, we have in chromatography we have a stationary phase and a liquid phase. In this case, the stationary phase is actually a chiral stationary phase which has affinity for any one of the enantiomer. So in a chromatographic, like this stationary phase, we effluent, or the mobile phase is your racemic mixture is loaded onto the column. And the column we have already a chiral stationary phase, and we add our racemic mixture. So and through an eluent means any solvent depending on the what type of compound we are taking. So now among these two enantiomers, suppose S enantiomer has binds to the chiral stationary phase more as compared to R enantiomer. So in that case, R enantiomer will be uh, uh, that will come fast or effluented fast in the column, that would reaches the bottom of the column first, then your S enantiomer will come. So in chromatographic separation also, chromatographic method also, you can separate or resolute your racemic mixtures. Then some kinetic methods, through kinetic methods also you can resolute your uh, racemic mixture. Suppose we have two enantiomers, a racemic mixture of these two enantiomers. We carry out a reaction in which one of the enantiomer is reacted to give the product very fast, and the other one is very slow. So in that case, this one we will obtain this one is with purity, with optical purity, because the other isomer is reacted to give you another product. So you get this one with very good purities. For example, in this substituted your benzyl alcohol, that is a racemic mixture. This is your classical kinetic reaction. This is also known as your oxidative kinetic. No, here not oxidative, we would come to it. But here, this OH group is esterified. So among this, if we are taking one enzyme, only this isomer where we have this OH group on the dashed wedge. Okay, that configuration of this OH group, that one will only react to form this ester, and the other isomer remains, the other enantiomer remains unreacted. So this one would give you very good purity, optical purity, and you can just go back to this one by doing your transesterification, so that you would get, if this one is R, this one is S, if you again you get your S alcohol by just doing transesterification. So what is the criteria of optical purity? How we uh, calculate it? So there is one term that is known as your enantiomeric excess. So excess of a single enantiomer divided by your entire mixture into 100% is known as your enantiomeric excess. And percentage enantiomeric excess, so you have to check the total moles of both the enantiomers, how much we have get, moles of one enantiomer minus moles of other enantiomer, that gives you 100%. 100 into 100, that gives you percentage enantiomeric excess. Or in terms of specific rotation also, you can just see specific rotation of the pure enantiomer, what is the specific rotation of the pure enantiomer, and what is the observed specific rotation. Suppose we just do a reaction in which we get 50% of this one R, and oh sorry, 60% of R and 40% of S. Okay, so if it is, this one is your enantiomeric, this one is in excess. So if this R enantiomer, the exact pure enantiomer, has an optical rotation of suppose X, and this one is the optical rotation that gives us less than X, must be, it would be less than X, suppose that would be Y, then enantiomeric excess would be Y by X into 100. Or suppose I just write it, if it is giving you, the pure enantiomer gives you 50-degree rotation, and the impure one would give you 10 rotation, then it would be 10 into 50, 10 by 50 into 100. And in case of this, from moles of enantiomer, which we can do it by through chiral GC, or we can just check the optical rotation. So in the progress of the reaction, if you just do in case of your chiral HPLC or GC, that will give one enantiomer will come first, the other one will come like this. So from this area, we can know the moles of this one. Suppose, as I told, one is your 60%, the other one is 40%. So the enantiomeric excess would be 60 minus 40, that divided by 100. I have just done it in percentage. We can do it in moles. So that is going to give you 20%. enantiomeric excess. Uh, so I think this is about your configurational isomers, where we have assigned configurations to your chiral centers by RS and racemic mixture also. I think we would take a break here for 5 minutes if it is okay. Or if you have any doubt, you can just ask me up to this. Can we take a break here?
Yes, ma'am.
Okay. Anyone is having any doubt?
No, ma'am.
Okay, okay. 5 minutes break.
Okay, okay, ma'am.
Okay. So I will join another 5 minutes around 7:40. We will then continue our present discussion. Okay, hello everyone.
Yes, ma'am.
Yeah, we can start again.
Yes, ma'am.
Okay, I'm just sharing my presentation. Next is our conformational isomerism. Before we have done our configurational isomerism, in which we have geometrical. We have not studied geometrical much. We will do it in the next class. We have studied mostly about our optical isomerism, and now we have our conformational isomer. So what is a conformational isomer? Which is the spatial arrangement of atoms or groups in a molecule are called conformations. Like if we can rotate, just use imagine yourself, we have different positions. Okay, but we are the same person. So this is our conformational isomers. In some form we are stable, like this one. We can just say, okay, this one is a stable form of ours, but this is the most unstable form of ours. But still, uh, all the like our hands, legs, all are intact as it is in this one. But suppose you see about a configurational isomer. So suppose our legs are in the place of our hands and our hands are in the place of our legs. So that is a different, uh, that would be a different molecule, or that would be a different like arrangement. So configuration and conformation is mostly when we can just go from one isomer to another by just simple rotation around a bond. But configurational isomer, we cannot just do like that. For changing a configuration means we always have to change that bonds by change the bonds by, or we have to break that one. Just I give the example, in the place of your hands you have to put your legs. That is a different configuration of yourself, but these are all the different conformation of yourself. So changing of configuration of a molecule always means that the bonds are broken. So a different configuration is a different molecule, but conformation means it is the same molecule, but you have getting different conformers or different isomers just by rotating it. You are not breaking it, you are just rotating around a single bond. So conformation of a molecule are readily interconvertible by your rotation atom bond, and all at the same molecule. But configuration is a different molecule. You cannot go from one configuration to another just like that. You have to break the bond, or you have to do some chemical, most you have to break the bond by chemical means or whatever. So as you just see, these two are different configurations. Okay, here if it is R, this one is S. So from going to one enantiomer to other, you have to first break this bond, because as we have, in case of resolution, we have just seen that we have to remove this one by forming a, means we have to see, and first we have to go to a ketone, then we have to put a chiral reagent so that we would get this one. So we have to break the bond. But if you just see this one, if we just rotate through the, we are not doing any thing with this carbon, just we are rotating this bond, so it is giving us a different conformation. This is the same isomer, but in different conformation or different conformers, different it is just rotated. So you can rotate the bond by 360 any degree, from 1 to 360. So there, that gives you conformational isomers. So first, the simple one, we would go for the conformation of ethane. So for conformation of ethane, we have discussed in case of our Newman projection formula, we have mostly two forms. We have different forms, but we just the most stable form and the most unstable form, means having higher energy and a lower energy. So one is our eclipsed conformation and one is our staggered conformation. As you can see, in case of your eclipsed conformation, if you just see from this carbon, this hydrogen will eclipse this hydrogen. Just for representation, we are seeing this. If you have just seen any models, you can see it in YouTube also. So this hydrogen is being eclipsed by this hydrogen. You cannot see that one. So that means you will have some steric hindrance here. So that eclipsed conformation is of higher energy as compared to your staggered conformation. So in case of ethane, we have two conformers. One is your staggered, one is your eclipsed. And from staggered to eclipse, it can just go by your 60 degree. If you rotate See, this is your staggered conformation. If I just rotate it by 60 degree, we will get your eclipsed conformation. So uh, you see, in each 60 degree, from staggered to eclipsed, again eclipsed to staggered. So in case of ethane, we have two conformations, and this energy barrier is not very much. This comes around 2.9 kilojoules per mole. So at room temperature also, your ethane molecule, most of the ethane molecules will be in staggered state, but some will be in your eclipsed state also. So they you cannot distinguish them because the energy barrier is very less, that is 2.9 kilojoules per mole. Just you see, this is the in case of your uh, staggered one, and this is your eclipsed one. You cannot see the back hydrogen. So this is your dihedral angle, like the front carbon, how much dihedral, we are changing the dihedral angle from 60 to 360. So this is your dihedral angle. Okay, so next comes your conformation of butane. In case of butane, we are just seeing through, this one is carbon number 2, and the back center is your carbon number 3. This is carbon number 1, this is your carbon number 4. So we can have, here we can have many conformations in your eclipsed and staggered form. Just first see, in your eclipsed form, this is highly eclipsed, methyl group are on the same side. If you just rotate it through 60 degree, this gives you a staggered conformation, but still this methyl is nearer to this methyl. So this would be of less energy as compared to this, but this is not the least stable. Then if you rotated this one, then it will go to again the eclipsed conformation. And when you again rotate it through 60 degree, here you just see the methyl groups are just opposite to each other. So this is going to give you the most stable conformation, that is your anti-periplanar. And this one would be your uh, uh, gauge conformation. This is your anticlinal, or this is, we can just say, eclipsed. So in total we have 1, 2, 3, 4 different conformations of butane. One is your syn periplanar, that means that is the most eclipsed form. Then the staggered form, which is the methyl group, it just adjacent it in a staggered conformation, but still you have some steric hindrance, so that gives you a mm, lower energy, that is your gauge form. Then again eclipsed form, but still this is of a higher energy as compared to gauge, but lower energy as compared to your this eclipsed 0 degree rotation eclipsed conformation, or your syn periplanar. And when this methyl, both the methyls are opposite to each other, that gives you the most stable conformation, that is your anti. And again you rotate it, you are going to get again your syn periplanar geometry. So you have syn, then gauge, then your again eclipsed, anti, again gauge, eclipsed, then gauge. So you can just, by rotating, you are going to get all the four conformations of your butane. So butane has these four conformations. Next comes your cycloalkanes. Okay, carbon. We know that tetrahedral carbon, or when carbon is attached to four different groups, the bond angle should be 109 degree 28 minutes. So when we are putting it in a cyclic form, so they come under some kind of strain. Like when it is, the ring size is 3, then when ring size is 3, the bond angle should be 60. So it has a strain of 49.5. Similarly, cyclobutane, the bond angle, in case of cyclobutane, the bond angle is 19.5. So according to Bayer strain, that molecule would be. But if you just see the most, in that case, the angle strain in case of cyclopentane is the lowest. That means this one should be the most stable conformation. This one should be the most stable cycloalkane as compared to your higher alk. But if you just see the per CH2, that is your heat of combustion per CH2 group, then you just see that cyclohexanes and the higher cycloalkanes are more stable as even as compared to your cyclopentane. Then comes your Sachs More theory, that is your theory of uh, strainless rings. That means to avoid your angle strain because Bayer has considered all these cycloalkanes to remain in one plane. So uh, according to this theory, to avoid angle strain, the molecules no longer remain in plane. They are puckered. Like for example, your cyclopentane, that is not, the structure is not like this, rather that is not in a plane, rather this four carbons are in one plane and the one is top plane. So this gives you an enveloped type of structure. Here you do not have angle strain, but if it is present like this, then here you have a eclipsed conformation, so which is more strain. So here you have two type of strain. One is your angle strain. Not only angle strain matters, also your torsional strain also matters. So torsional strain is when, that is because of the position of your hydrogens or whatever groups in an eclipsed manner, that gives you a torsional strain. So in that case, to overcome those strains, not only angle strain, also torsional strains, the molecules are no longer remain in plane but they get puckered, means that get twisted. That would give a different conformation, different type of structure. So this cyclopentane that gives you one envelope, open envelope type of structure is more stable as compared to your planar structure. So next, which is your cyclohexane, we would see the conformation of cyclohexane. In case of cyclohexane, there also the cyclohexane no longer remains in a plane. It has many conformation, among which one is your chair conformation. If you just see this chair, it is like these four carbons are in the plane here, and one carbon is up and one carbon is down. So this is the chair conformation of cyclohexane, which is the most stable conformation of your cyclohexane. So if we just check the Newman projection, in this case, you just see all substituents are anti to each other, that is they are in the staggered conformation, all are in the staggered form. So in that way, this chair conformation of cyclohexane is most stable conformation. So there are many different conformation of cyclohexane, among which you have a boat conformation and a twist cyclohexane, twist boat, and also half chair conformation. So in case of your boat conformation, you just see there are two hydrogens which is known as your flagstaff positions. So these flagstaff positions here, they are eclipsing each other. So this uh, projection is of very high energy because this is a eclipsed conformation, not your staggered conformation. Similarly, in case of your twist boat, if we just twist it, the eclipsed conformation is a bit relaxed, so you get a more stable conformation as compared to your boat conformation. So the ring okay, so here there is a in case of cyclohexane, we have these hydrogens, these positions. One is your axial position, one is your equatorial positions. So if you just think that if we have two different type of hydrogen, because this every in each position you have an axial hydrogen and one equatorial hydrogen. So in NMR you are going to get two different kind of protons, but actually this does not happen. You get only a single proton because they undergo ring flipping, ring inversion, or that is known as your flipping from one form to another form. So when flipping from one to another, it has to go through these conformations from chair to half chair to twist boat, half chair to chair. So these are the different conformations of your cyclohexane. So chair conformation is the most stable conformation, and half chair here it is the most more energy is required, so that is of higher energy. Then twist boat is a less energy. True boat structure is a bit more energy. Twist boat again less. Then half chair, then chair B. So from one chair form to the another chair form, if you just see, it was the HA was in axial position and HB was in your equatorial position. But by ring flipping, this HB has come to your axial position and this has come to your equatorial position. And this cyclohexane, as we see, it has many conformations like your chair form, half chair, twist board, true board, twist board, half chair, and chair. And this only requires from chair A to half chair, it only requires 43 kilojoules per mole. So which is actually sufficient in your room temperature also. So you get two these conformations in case of your cyclohexane. And in cyclohexane, as I told, every while writing a cyclohexane, you just the chair conformation, these two should be parallel. Put a slanting line, and this should be parallel, and this one should be parallel, and this one should be your parallel. Okay, and here you have your equatorial hydrogen, and this is axial, equatorial, axial, equatorial, axial, equatorial, axial, equatorial, axial, like this. So you have equatorial position as well as your axial position. Okay, so we would come to now your substituted cyclohexanes. So you just see these hydrogens, one equate, these are your, this is equatorial and this one is your axial, but this alternate, these hydrogens are all up relative to their partners on the same carbon atom. Okay, and these red hydrogens are all down relative to their partners on the same carbon atom. So when we put a substituent on your uh, cyclohexane, instead of hydrogen we put a substituent. Suppose we put a substituent at X at your axial, removing the axial hydrogen. So this axial hydrogen, removing your axial hydrogen or axial substituent, immediately undergoes inversion or ring flipping to give so now, as we know that the after the flipping of your cyclohexane, the axial hydrogen will become your equatorial and equatorial will become your axial. So this will immediately form your equatorial substituent. The substituent would be now in your equatorial position. So this conformation is actually lower in energy. So the if you just see, the equilibrium is more towards this side where the substituent is present in your equatorial position. The reason is, if it is present in your axial position, so if this is 1 2 3 4 5, so this is known as your 3 5 diaxial interaction. So the hydrogen present at carbon number 3 and carbon number 4, that is at the axial position, it does not get repulsion from your equatorial groups, but from the axial hydrogens it face repulsion, steric repulsion. So this is an unstable, very unstable situation as compared to when it is present in your equatorial position. So equatorially substituted cyclohexane is more stable as compared to your axially substituted cyclohexane. If we just see in case of our Newman projection formula, you just see this is your equatorial when the halogen or any substituent is present in your equatorial position. So that this one and this carbon, they are anti-periplanar, that is they are staggered in a staggered conformation. But when that is present in your axial, in your Newman projection formula, you just see these are your axial and these are your equatorial position. So when it is present in your axial position, so there it is in a you just see there you have a gauge interaction. So that is a kind of eclipsing interaction. So this one is less stable, this one is more stable. So first of all, whenever we have a substituted, mono-substituted cyclohexane, it mostly prefers to stay in your equatorial position depending on the substituent. Also, we just see so in case of methoxy cyclohexane, you just see the difference between axial and equatorial conformer is very less. The reason is our methyl group is away from these hydrogens. But in this case, we are getting more interaction. So here, the depending on your groups, if you have a tertiary butyl group, then the energy difference is very high. So equatorial substituent is having more. There is more percentage of your equatorial substituent conformer as compared to your axial conformer. So depending on the group, there is your energy difference and there is the percentage of equatorial substituent. But still, you just see any group, the equatorial substituent is having more percentage as compared to your axial substituent. So when comes your di-substituted cyclohexane? So when comes your di-substituted cyclohexane, we have relative to this one, we have now three positions. If this is one, we can have one, two, three, four. So either the second substituent can go to position number two, three, or four. So first we will check in case of your 1,4-cyclohexane diol. So these OH groups, when both, if this is in the plane of the paper, if both the OH groups are on the same side, we will say cis. If they are on the opposite side, we will just tell them as trans. So now we have two, this is your geometrical isomer. Okay, so now we have two configurations, cis and trans. Okay, in case of 1,4-cyclohexane diol, we have two configurations. Now this configuration, cis configuration and trans configuration, would have different conformations. So in case of cis 1,4-cyclohexane diol, both the OH, one OH group can be on the axial side and one OH group can be on the equatorial side, because we know that these two OH groups are on the same side, axial and equatorial. In case of 1,4 relationship, axial and equatorial are on the same side. So now either one OH on axial and one OH or equatorial, or it can just flip, this OH will go to axial and this OH is going to be your equatorial. They both are same. Okay, so there would be your 50-50 percentage. But in case of your trans means one would be up, another one would be down. So in that case, one would be, both would be axial or both would be your equatorial. So when both are equatorial, we know that whenever we are putting a substituent in the equatorial position, that is more stable. So you just see the equilibrium lies more towards the conformer where both the OH groups are in the equatorial position. So in case of the in case of trans 1,4-cyclohexane diol, both are equatorial. Here we have one axial, one equatorial. Okay, in case of 1,3-di substituted, here also we can have cis as well as trans. So when 1,3-di substituted cyclohexane, so here this 1 and 3 position most, when it can be either axial or equatorial. So more stable would be your equatorial. And in case of your trans, one is equatorial, one is axial, so there is equal chance of EA or AE. So here it is your AE. And 1 2, in case of 1 2, we have again two configurations. One is your trans, one is your cis. So in case of trans, both can be equatorial or both can be axial. So here your both would be, there is no, so both are equatorial. So this one is not favorable. But when, in case of your cis, in case of cis, we have, here you just see we have two different type of groups. One is bromine, one is OH. So one bromine can be equatorial and this can be axial, or this is equatorial and axial. So in this case, as bromine is a bigger moiety as compared to OH, so in that case bromine should present in your equatorial position, because bigger moiety face more axial interaction as compared to your smaller moieties. So it will prefer to be in a position where there is less diaxial interaction. So the equilibrium would be more towards this one. That means bigger moiety would be in your equatorial position. And in case of this isomenthal, here in case of your tri-substituted one, you have to always put in such a way that this isopropyl, that is the bigger moiety, in your equatorial position, then give the other priorities. Always put the bigger moieties in your equatorial position, then check this. Suppose in this case, okay, so in this cis, so this both can be, one can be equatorial and one would be your axial. So in that case, this is the only conformer in which your this bigger moiety is present in equatorial and this one is your in axial. Next, when we have a sp2 hybridized carbon in your cyclohexane. So that gives us cyclohexanone and cyclohexane. Okay, so this double bond can be exo or this can be endo. So whenever we have a endocyclic double bond, in that case the half chair conformation is more stable as compared to your chair conformation, in which your carbon number 1 2 3 4 are in a same plane, and one is up the plane and one is down the plane. And in case of your cyclohexanone, there also we get a uh, the cyclohexanone. Uh, if we have a substituent at carbon number 2 or carbon number 3, okay, in that case the axial group, if it is in a axial position, then it would be more stable as compared to any normal cyclohexane where your CH3 group is in your axial position. The reason is, in this case this CH3 group does not have more, only one diaxial interaction is there. There is no, we do not have the other hydrogen for your diaxial interaction. So in that case, that is known as your 2 alkyl keto effect. And whenever we have a substituent like halogens in our cyclohexanone, in that case actually the halogen, the more preferred one is halogen present in your axial position. Why this kind of ambiguity, like the reverse? In this case actually whenever your halogen is present in a axial position, as compared to your equatorial position, if it is present in your equatorial position, there will be steric hindrance of these electronic clouds. You know that halogens are more electronegative element, again oxygen is more electronegative element, so there would be more repulsion among the electrons here. And again there would be dipole interaction. And if it is present in your axial position, so the sigma star of your X can overlap with the pi overlap to give this kind of moiety, and this stabilizes your molecule. So whenever one halogen is present or you have a substituted halocyclohexanones, then the halogen prefers your axial position, not your equatorial position. Then we have fused rings, that is two rings are fused with each other. So one is your decalin, where your two we have two rings, and two carbons are common to these two rings. So two, we can just see two cyclohexanes are actually fused with each other, that is known as your decalin. So these two carbons, okay, this fusing can be done in two manners. If both are actually joined on the same side, or we just say one is axial, uh, cyclohexane's axial hydrogen is removed and that is attached to another carbon, and in this case equatorial hydrogen is removed and that is attached to another carbon, that gives you cis decalin. Or if both equatorial hydrogens are removed and attached to carbons, then that gives our trans decalin. So decalin have two configurational isomer, not conformational. We have two configurational isomers, that is your cis decalin and trans decalin. Now this cis decalin is interconvertible by your ring inversion, like this ring inversion, to give you another cis conformer. But this trans decalin, here you cannot have your uh, ring inversion is not possible, so you have only one conformational isomer for transdecalin, because as you see this, in case of transdecalin, these carbons are bonded with the first cyclohexane through its equatorial position. So to flip the ring, these two hydrogens, now this, it has to attach in your axial fashion, so which is not possible to join two axial positions into six membered rings. So transdecalin has only one conformational isomer, but your cis-decalin has two conformational isomers. So just remember, cis-decalin and transdecalin, they are configurational isomers, and cis-decalin can interconvert with its other isomer, other conformational isomer, but transdecalin cannot invert it, so it cannot be converted to other conformational isomer of this one. Again, substituted in case of your substituted decalin, if we substitute the decalin by an OH group, that gives us now 3 stereogenic centers, and if we substitute it by one double bond O, then that gives us 2 stereogenic centers here. So what are the chiral center we see if you substitute it by OH group, that is your decalol, this one is your decalone. So here we have 3 stereogenic centers, and we know that the number of stereoisomers possible is equal to 2 to the power n. N is the number of stereogenic centers. So in case of your decalone, uh, we have uh, we can have now cis decalone and trans decalone. And so cis decalone and trans decalone can exist in two forms, mirror image of each other. So these are your enantiomers. And in case of cis decalone can interconvert with its other conformational isomer, uh, and this cis decalone, these two are the mirror images, and these two are the mirror image of each other. Similarly, in case of your decalol, we can have trans decalol, and again trans decalol, both OH group can present in the axial. So this is one conformational isomer, and the OH group can present in your axial. So we have two different trans 2 decalol. One is your axial, one is your equatorial. So these two are two stereoisomers, the mirror images. These are the enantiomers. These two are your enantiomers. And even cis 2 decalol can have your equatorial and axial, but in case of cis, as we know that there can be ring inversion, so the equatorial OH group can convert to axial, and axial can go back to your equatorial. So after this, we have just studied the stereochemistry of molecules whenever we have a chiral center. Like our glyceraldehyde, L-glyceraldehyde, D-glucose, L-glucose, we have studied enantiomers, diastereomers. Then we come to our conformational isomers. So there are some chiral molecules. Those are actually asymmetric molecules. Now we will deal with our dissymmetric molecules, where we do not have a chiral center, where we do not have a means improper rotation axis, but still we have a simple axis of rotation, and we do not have a chiral center here. So first class is your allenes and spirines. So in this allenes, allene means here you have carbon double bond, again double bond. So this carbon is your central carbon is your sp hybridized, and so px orbital of this one and px orbital of this one are overlapped, and py orbital of this one and py orbital of this carbon overlap. So these two double bonds, these two pi bonds are perpendicular to each other, as we know that px orbital is perpendicular when, so this, if this is your py orbital, this is your px orbital, so they are mutually perpendicular to each other. So these two pi bonds are mutually perpendicular. So now there we do not have any chiral center, but still we have a chiral axis here. How? So in case of allenes, if both these if these substituents are same, we have a plane of symmetry. If we just go through this hydrogen chlorine and this one, then we have a chlorine on both the sides, same. So these are your achiral allenes. If these two substituents are different, so then it is not uh, same, or this is not symmetrical, so we do not have a plane of symmetry. So in that case, this molecule behaves chiral. This is a dissymmetric molecule, but still we have a chiral C2 axis, and this axis is known as your chiral axis, and these are optically active. So for this is also known as your axial chirality, and for this allenes to be optically active, the substituents on the terminal carbon should be different. This means this carbon substituent may be same, but on the same carbon the substituent should be different. So these are all the achiral allenes. Just you see, if we have this, these two may be same, but here if these two are same, then we have a plane of symmetry here. Okay. If neither of the ends are attached to two identical substituents, then it is chiral, such as these are all your chiral allenes. So how we assign configuration in allenes? So the molecule is viewed along its axis and the relevant substituents are projected onto a plane at right angles to the axis. The groups are prioritized using the sequence rules with the extra proximity rule, which requires that near groups precede far groups. For example, if we are just viewing it from this side, okay, from this side, if we just see, first you have to, so this one is your our near carbon, okay, near groups. So we just put a circle here. Okay, this is the front carbon, and these are the groups on our front carbon. And if we just see, and the back carbon are put as a vertical, as a horizontal line here. Now we would put our groups. So as we see along this axis, chlorine is on our left and or is on top and bromine is on down. So I put chlorine on top and bromine on down. And if we again see from this, hydrogen is on the left side and CH3 is on the right hand side. So hydrogen is on the left side and CH3 on the right hand side. And here you have to see that on whatever we don't whatever group we are in the front carbon, they are given as priority number 1 and 2. So this is priority number 1, this is priority number 2, whatever be the group, whatever we are viewing it along this direction. So in that case, bromine is your priority number 1 and chlorine is your priority number 2. And hydrogen is on the left side and CH3 is on the right hand side. So this one is 3, this one is 4. And when we trace it from 1 to 2 to 3, if it is clockwise, then that would be R, A should be written here. And we do not have to change the, like, whether it is in the vertical and horizontal, that doesn't matter here. We just put R axial, and if it is counterclockwise, it is R S axial. Suppose you say, I won't view it from this direction, rather I will view it from along this direction. So if you are going to view it along this direction, so you just put a circle here, and so this one is our front carbon. So now this is priority number 1, this is priority number 2, this is priority number 3, this is priority number 4. From which side we are viewing, those two are given the highest priority, and depending on their atomic number. So these two are given higher priority, and as this one is more priority as compared to hydrogen, so this is 1, this is 2, and this will given the lower priority 3 and 4. And as we just see, CH3 group, if we view along this direction, CH3 is on the left side and hydrogen is on the right side, and chlorine is on again top and bromine on down. So here also, if we just trace the path from 1 to 2 to 3, then also we get the R. So whether you are viewing from along this direction or you are viewing along this direction, that is going to give you the same configuration. So in case of allenes, you have to view it along any direction, then assign your priorities. The first near groups always precede the far groups or the back groups. So whatever groups you have in which side you are seeing or observing, in that case the priority, those would be given priority 1 and 2, and the far groups would be given priority 3 and 4. Okay, so we obtain the same configuration when a particular isomer is viewed from any side of the chiral axis. Even in case of spirens or spirens, that is a actually uh, these are two ring compounds, and both are actually only one carbon is the common carbon in that case. So you, those are known as your spiro compounds. So in this case also you have a axis of symmetry. So this one is a axis of symmetry. If you have different groups attached here, then those would behave chiral, but these are not chiral. So if you have different groups, then you have a chiral axis here. For example, in this case, in this spiro compound, we have different groups. Okay, and we can just assign the configuration as we have done in case of your allines. If we view from this side, NH2 is on top and hydrogen is on down. So this one would be 1, 2, and this one is your 3, 4. NH2 on top and hydrogen on down, top and down. And if you view from this side, NH2 is on the left and hydrogen is on right. Then you trace the path from 1 to 2 to 3 as it is giving you clockwise, then that is R. Similar, so allenes and spirins, you can just give the same kind, assign the same kind of configuration. Next comes your alkylidine. These are also the having your chiral axis. These are also the molecules where you are having a chiral axis. You don't have a chiral center or any carbon. We know that carbon having 4 different groups are known as your chiral. So here carbon is your chiral center, but here we do not have any chiral center. But because of the presence of a chiral axis, we are having enantiomers. So if you just see this, this is the these two are actually enantiomers and they are not superimposable. Okay. Similarly, you have biphenyls. In biphenyls, when both the benzene rings or aromatic compounds are joined by your carbon-carbon single bond. Okay, so in carbon, as we have a carbon-carbon single bond, there is free rotation here. So you have different conformations. So from one form to another form, it can easily, you can just, it can undergo from one form to another. But if you have only you have hydrogens or very small groups, then these are on the same plane. But if you have a bigger group here, then that will have steric hindrance. So now this one will no longer remain in the same plane. So here you have also a chiral axis. So due to the restricted rotation about the bond, linking the two phenyl groups due to steric hindrance between bulky ortho substituents. So this that gives two different isomers. They are not now resolvable. That means they are two different enantiomers. So this type of isomerism is known as your atrope isomerism. So mostly whenever you have a chiral axis, in case of your biphenyls, that is known as your atrope isomerism. So atrope isomerism are stereoisomers arising because of hindered rotation about a single bond where energy differences due to the steric strain or other contributors create a barrier to rotation that is high enough to allow for isolation of individual conformers. Okay, they are conformers, but now they are, you cannot means rotate it because of their steric hindrance or any kind of hindrance. So now you have two different isomers. Those are your optically active isomers. So what are the conditions to show enantiomerism for biphenyls? Each ring must be unsymmetrically substituted. If it is symmetrically substituted, both hydrogen here or CO2H, then that is not enantiomers, that don't give. Both rings must be substituted in ortho position and the substituents must have a large size. If smaller size also, the barrier to rotation, the energy barrier to rotation is very small. So in that case, that would again and go back to the other isomer. So you would get a different type of, you would get a racemic. Okay, for here also you have to do the same kind of configuration. Assignment of configuration can be done as the same. So if you view from this side, you just see NO2 is in on top and CO2H is on down, and COOH is on the left side and NO2 on the right hand side. And while tracing the path, you go from 1 to 2 to 3, that is anti-counterclockwise, so that gives you S. There is another effect that is known as your burst tracing effect. Suppose we have CF3 groups here, still these are not resolvable because the energy barrier for this rotation is very small. So this again, this can easily get converted to its other isomer. But if we put in another substituent at the meta position, so now the steric hindrance, it would exert one effect on this CF3, so that the steric hindrance would be more and it cannot be rotated to its other isomer. So the energy barrier, that gives you more energy barrier. So now it is easily you can just resolve the both the enantiomers. Then we have done chiral center, chiral axis. Then we have a planar chirality. We have a plane, which is your chiral plane. Suppose in this case, we have mm, a plane. If we have different groups here, then that would give you a chiral plane. For example, in case of your cyclophanes, also ANSA compounds, here you have a chiral plane so that they can be resolvable. If we do not have these substituents, then you don't have a chiral plane, but whenever you have a different substituents here, you have a chiral plane here, not axis. Here you have a chiral plane. So chirality due to your planar molecules, chirality because of a plane. Okay. Then another class of your stereoisomers are helicins. What is helicins? Helicins are actually orthocondensed polycyclic aromatic compounds in which benzene rings or other aromatics are angularly annulated to give helically shaped. Like we know that our DNA, and they are like this helix, DNA helix, and so they are like okay, they are rotated, means it gives like this. They are not planar. So whenever we have ortho-condensed polycyclic aromatic compounds, they are angularly annulated to give helically shaped chiral molecules. So actually, for according to IPSC, that gives you a optically active compound, at least N is 5. Those are considered as helicins. So this is our hexahelicin. So one is rotated towards your left, towards, okay, and towards clockwise direction, and this one is your in your anti-clockwise direction, and these two are actually mm, optical isomers. They are mirror image of each others. You cannot interconvert them just by rotation. So these are because of the presence of this helical structure. So this, for helical structure, for optical activity, we have hexa, not we have this 4 helicin also we have, but those are not optically active. More than 5 you have, like this one. This is your M4 helicin. It has low energy barrier for racemization, so that one you cannot obtain the optically pure enantiomer. But after 5 you can get your optical isomers. As you can see, the optical rotation in this case is very high. So 5 helicin, 6 helicin, 7 helicin, 8 helicin. So this is your helicity, which is helical chiral. That is known as your helical chirality. That is because of their conformation in such a way that you cannot just separate their you can separate their enantiomers, or they are non-superimposable mirror images of each other. So next is cyclostereoisomerism. In whenever you have configurational isomers or enantiomers, in case of your cyclic forms, that deals with your cyclostereoisomerism. Suppose you have a monosubstituted cyclopentane, that is not chiral because you have a plane of symmetry. And if you have a, this one is cyclic, although this one is our okay, cis. So in that case also we have s, although both are different groups, but this is a meso compound because we have a plane of symmetry. Okay, but in this case you just see we have two different substituents, we do not have a plane of symmetry, so we can obtain two different enantiomers. Similarly, here also we have two different enantiomers and they are not superimposable. So these are chiral molecules. Similarly, in case of your adamantane, if you just see here, this floor we have these four groups are attached to four different carbons, not attached to the same carbon. But if we join, it is in the center of the adamantane, and that gives you four different groups. It seems like there is an atom present in the center and four different groups are attached in an tetrahedral fashion. So for this one is optically active, but here you do not have a carbon center, or so there is no chiral center, there is no atom center which is chiral, but rather we have a center which is chiral, but there is no atom present here. So here you do not have a chiral center. That means you do not have a carbon atom which is chiral, but you have a axial of chirality. So to summarize, today we have discussed with molecular symmetry and how molecular symmetry and chirality are related. Like we know that if we have a uh, plane of symmetry as well as your simple rotation of symmetry, that is not a symmetric molecule. So those are that is a symmetric molecule. Those are not optically active. But if you have a only plane of symmetry and no alternating axis of symmetry, that one is a dissymmetric molecule that is optically active. And when you do not have any kind of symmetry, that is no plane of symmetry, not any alternating axis of symmetry or rotational axis of symmetry, then that is your asymmetric compound, or those are your optically active molecules. Then this stereoisomerism of molecules with chiral centers, we have discussed configurational, conformational. In configurational, we have discussed RS nomenclature, racemic mixture, diastereomers, enantiomers, and in conformational isomerism, we have studied about the different conformations of alkanes and cycloalkanes, and what are enantiomers and stereomers, how we assign configuration. And we have done stereochemistry of molecules without chiral centers also, which include our allenes, spirins, cyclophanes, helicins, etc. So now we just see we have four different type of chirality. One is your central chirality, where we have a central carbon and four different groups are attached to it. Axial chirality, where we have a axial chiral axis here, mostly in case of our allenes parents. And we have a planar chirality, where we have a chiral plane, and helical chirality, where we have a helicins in case of our helicins. So this is the summary for today's class. Next Monday, we will discuss about this your unit 2, which includes configuration, topicity, asymmetric induction, how we are carrying out reactions, what are the principles behind it, and how this configuration, we can determine the configuration. So we will deal with all those things in the next class. So thank you for listening. So if anyone is having any doubt, you can just ask me.
No, ma'am. Thank you, ma'am.
So is it like you could understand everything, or I am being bit fast?
Yes,
Because I
ma'am. Understand. Understand.
okay, because I have to cover the in 2 hours. I have to cover a lot of things. So just whenever you have any doubt, you can just like stop me and ask any of your questions.
Mm, ma'am, kindly discuss about the plane of symmetry of benzene.
Benzene molecule is a planar molecule. Okay.
Yes, ma'am.
Yeah, that is, you have like six-fold axis C6. Okay, again, so that is, if you just learn about the point group, so that is a D6H, I think. That is a planar molecule. So there would be no stereoisomers in that case. Okay, so
Ma'am, is
only,
there any diagonal plane? Sigma
yes,
D.
you have a diagonal plane also. Okay,
Sigma
sigma d.
D, sigma H, or sigma B?
You have sigma b, sigma h, sigma d. You are having all those planes. So that mostly covers actually in your group theory, but you have all those things. Okay, that
Okay,
is a
ma'am.
very kind of planar molecule.
Thank you, ma'am.
Yeah, most welcome. So on Monday, we will discuss the unit 2. You just go through your materials, whatever is given to you. I am mostly dealing with those materials only. So we can discuss on Monday also. If you have any doubt from today's class, we can discuss on Monday also. Okay.
Okay, ma'am.
Yeah.
Thank you,
Okay.
ma'am.
Yeah, most welcome. Have a good night.
Good night, ma'am.
Good night.